Everyone, today in this video we are going to see next type of microwave passive device. It is called as directional coupler. Okay, we have seen tees, ring, waveguide. Now we are going to see direction coupler. What is the use of direction coupler in the microwave circuits? So what is a directional coupler? It is a device that samples small amount of microwave power for measurement purposes. The power measurements include the incident power, reflected power, VSWR values, etc. So when we want to measure a power at a particular point in a microwave communication circuit, we use directional couplers. Okay, on your screen you can see the diagram where our directional coupler is shown. As you can see, there are 4 ports, so it's a 4-port waveguide junction. Upper 2 ports are primary waveguide forming primary waveguide, and lower 2 ports are forming secondary waveguide. Okay, so let's see. Directional coupler is a 4-port waveguide junction as shown in figure. As I said, it consists of primary waveguide formed by port 1 and 2 and secondary waveguide formed by port 3 and 4. Okay, when all ports are terminated in their characteristic impedances, then there is a free transmission of power from port 1 to 2. That is, free transmission means without any reflection power will be transmitted because they are terminated in the characteristic impedance, so maximum power transfer will happen. Then there will be no transmission of power from port 1 to port 3 and port 2 to port 4 because there is no coupling between 1 to 3 and 2 to 4. So let's look at that in terms of diagram. So port 1, let's say it is applied an input power, it is called as incident power. Entire power will transmit to port 2, let's call it PT, transmitted power to port 2. No reflection, so entire power will be transmitted. Now some of that power will be sampled and taken out at the port 4. Okay, so at port 4 we will have forwarded power, which is a sampled power. Okay, and at port 3, if it is possible, we can have a backward power. Okay, now this is a maximum transmission between 1 to 2, free transmission, no reflection. Between 1 to 3, no transmission because there is no coupling. Also between 2 to 4, there is no transmission of power because of lack of coupling. Okay, so that is how this measurement device works. Now let's see what are the characteristics of this directional coupler which are useful in communication circuits. The characteristics of this coupler can be expressed in terms of ideally 2 parameters. Third one is also possible. These are coupling factor and directivity. Third one is isolation, which is also considered in many cases. So assuming that wave is propagating from 1 to 2, as I said, so let's draw. This is 1, this is 2. Wave is transmitting from 1 to 2. This is 3, this is 4. Then coupling factor can be given by, this is obviously expressed in terms of decibels, that is dB. So 10 log 10 is for conversion to decibel into 10 log 10 of P1 upon P4. That means P1 is here, so it is also called as Pi, and P4 is Pf. So incident power upon forward power gives you coupling factor. Now directivity, again it's mentioned in decibel or expressed in decibels. It is a ratio of P4 upon P3. That means for directivity, forward power upon backward power. So what do these 2 parameters indicate or characteristic indicate? Pi upon Pf indicates how much of a incident power is coupled to the secondary waveguide because P4 is in secondary part of waveguide, and directivity indicates how much of a incident power is coupled to the all ports of the secondary waveguide. Okay, ideally for third port power should be 0, but practically it does not exist. 0 value does not exist, so P3 is not always 0 practically, but ideally if you consider P3 will be 0, so directivity ideally it should be infinite. Okay, so let's see. It should be noted that port 2, 3, 4 are terminated in characteristic impedances, so there are no reflections because maximum power will transfer. So the coupling factor is measure of ratio of power levels in the primary and secondary lines, how much is inputted to primary and how much is available in the secondary. Hence, if coupling factor is known, a fraction of power measured at port 4 may be used to determine input power. Okay, so from that sampling we can understand or calculate how much incident power was at port 1. This is important because microwave power measurements because desirable for microwave power measurements because no disturbance which may be caused by the measurements occurs in the primary line. So what is the meaning of this statement? Now if we want to measure the power, let's see the diagram. If we want to measure the power, if entire power is transmitting from here to here, why don't we just measure the power here? Let's measure it here. But this value will be value of PT. If I want to calculate PI, I can calculate it here, but this will be value of PI. So what is the value of power inside the coupler during the transmission? So for that, what we can do, we have to attach a measurement device here. Now why can't we do that? Because when we attach a measurement device here within the primary waveguide, then it will cause electrical disturbances and we will not get accurate results. Remember, entire power should be transmitted to the second port. That is our intention. So if we insert a measurement device in between, it will cause electrical disturbances and entire power will not be transmitted to port 2. So what we are doing, we are sampling certain part of that power and getting measurements at port 4. Okay, that's why port 4 is useful for measurement of power. Moving on. Now all the passive devices in microwave circuits are characterized by the S parameters, but before going to characteristics, the directivity, as we have seen, is a measure of how well the forward traveling wave in primary waveguide couples only to the specific port of a secondary waveguide. So how much is wave is forwarded and how much is backfired. Ideally none should backfire, so P3 should be 0 and that is what it is desired. An ideal directivity for the directional coupler should be infinity. In other words, power at port 3 must be 0 because port 2 and port 4 are completely or perfectly matched. For practical cases, the directional coupler have directivity of only about 30 to 35 dB. So we are far away from the infinite value, but still it is a very good directivity considering circumstances. 30 to 35 dB is sufficient. So there are several types of directional couplers available in the market, such as 2-hole directional coupler, 4-hole direction coupler, reverse coupling directional coupler, which is also called a Schwinger coupler, and Beth hole direction coupler. Okay, there are many others which are recently manufactured also or invented also, but for introduction we will only look at the 2-hole directional coupler. So this is the diagram of different types of directional coupler. Diagram A denotes the 2-hole direction coupler. You can see there are 2 holes separated by length lambda g by 4. Lambda g is a guided wavelength. So distance between the center of 2 holes is a lambda g by 4. Similarly, second diagram, that is diagram B, showing 4 holes, that is called as 4-hole direction coupler. Lengths are different between each hole. Then Third diagram, diagram C, is a Schwinger coupler. That is what? Schwinger coupler is, let's look at again, the reverse coupling directional coupler. And fourth is a Beth-Hole directional coupler, which is having a rotated secondary waveguide rather than parallel secondary waveguide. So we are only looking at diagram A for current introduction. So let's have a look at a two-hole directional coupler. In a two-hole directional coupler, with traveling waves propagating in it are illustrated in figure. So let's assume we are applying a signal or wave at port 1. It will travel along a primary waveguide and arrive at port 2. So power available at port 2 will be Pt, which will be equal to Pi. Now there are two holes in the directional coupler. So when wave is traveling through the primary waveguide, it will enter through the first hole. From first hole it will go towards the port 4 and port 3. Again, when it further moves on, it goes from the second hole, again goes to the port 4 and port 3. The forward direction waves will get added at port 4 because they will be in phase, but backward directed waves will get cancelled at port 3 because they will be phase shifted. Okay, because of matching, perfect matching, they will get cancelled at port 3. Okay, the spacing between the center of two holes is given by 2n plus 1 into lambda g by 4, that is in terms of integer multiples of lambda g by 4. N is a positive integer. So as we have talked about, it is characterized by the S parameters. A fraction of wave energy enters into port 1, passes through the holes and radiated into secondary waveguides, as holes act as a slot antenna. So holes are acting as a antenna to radiate waves further. Then forward waves in the secondary guide are in the same phase as we have discussed just now, and added at port 4 and cancelled at port 3 because they are out of phase. The backward waves in the secondary guide are out of phase by 2L upon lambda g into 2 pi radians. So they get cancelled out at port 3. So the phase shift between the two waves is given by 2L upon lambda g into 2 pi radians. Okay, that is causing the cancellation of waves in the port 3. So that all four ports are completely matched. So how to characterize the S matrix of a two-hole direction coupler? Since all ports are completely matched, there is no reflection, and if there is no reflection, that means all the diagonal elements of S matrix will be 0. S11, S22, S33 and S44. And already at the beginning we have mentioned that between port 1 and port 3 and port 2 and port 4 there was no coupling. That means parameters, S parameters related to 1 to 3, that is S13 and S31, and S parameters related to 2 to 4, that is S24 and S42, both will be 0 because of no coupling. So our S matrix is reduced to this one: diagonal element 0, the S13, S31, S24, S42 are also 0, and remaining parameters are to be found out. We can further reduce this. Let's see how to reduce this matrix. Now if you observe, there are 4 ports in this. So because of 4 ports, the matrix is of size 4 by 4. Okay, so let's see how to reduce this. Equation of S matrix can be further reduced by the properties of S matrix, considering the first property, that is zero property. So what does zero property says? Let's consider this column and this column. So by zero property, what will happen? S12 into S14 conjugate plus S32, sorry, S32 and S34, S32 and S34 conjugate, this addition will be equal to 0. Let's see whether it is mentioned the same or not. Yes, S12, S14 and S32 plus S34 conjugate is equal to 0. Similarly, if we consider first and third column, S21 and S23 conjugate plus S41 and S43 conjugate is equal to 0. Or we can rearrange this or simplify this considering only the magnitude part, not the phase part. Then taking the second part onto the right hand side, we can say S12, S14, obviously their magnitudes are equal to S32 into S24, and again in terms of their magnitudes. Same thing applies to the second equation. This is using the zero property. And if we use the unity property, then what will happen? We will have to take each column one by one. So what will happen? Let's take second column again instead of first, for example. So it will happen, what will happen? S12 into S12 conjugate plus 0, then S32 into S32 conjugate. This will be equal to 1 because of unity property. Okay, when we are dealing with the same column, it will be 1. When we are dealing with the two columns, it will be 0. So let's see whether it is the same or not. So S12 into S12 conjugate, S14 into S14 conjugate is equal to 1. But symmetry property is also there. So what does symmetry property tells? What does the symmetry property tells? S12 is equal to S21, S14 is equal to S41, and S23 is equal to S32. That is, they are symmetrical about their, let's see, the matrix. These two are symmetrical. These two are also symmetrical, same, and these are all symmetrical. So because of this, we can mention this, and if we use all these three properties, we can write S12 is equal to S34 and S14 is equal to S23. How is this obtained? Now using the equations, let's say using these equations, now consider this one. S21 means S12 into S23 conjugate plus S41 means S14 into S43 conjugate means S34 conjugate. Okay, now compare this with this one. S34 conjugate is multiplied by S14 here, and here it is S32. So 14 is equal to 32. 32 is nothing but 23. So S14 is equal to S23. Or if we consider this one, S12 is multiplied by S23 conjugate. S12 is multiplied by S14 conjugate. So 14 is equal to 23. Same. Okay. Similarly, we can find out answer for S12 is equal to S34 also. So considering this, let's assume that S12 is equal to S34 is equal to same value, that is P, and S414 and S23 equal to JQ. Both P and Q are real. J denotes the imaginary part. So if we assume that, how can we reduce? Let S12 plus S34 is equal to P. So from second equation of zero property, what is the second equation of zero property? Sorry, this is the second equation of zero property. So what we have assumed, this is P. So this is P into S23 conjugate, and S34 is this one. So this is again P. P into S41 or S14, that is equal to 0. So substituting that, what we are getting, P into S23 conjugate plus S41 is equal to 0. So similarly, if we assume S23 is equal to S41 is equal to JQ, then we will get same type of equation. and from equation of unity property we can obtain p square plus q square plus 1. So our assumption will remain valid. So if we assume these numbers, then our S matrix will be reduced to this one. So S12, S23, sorry, S21, these are real, this is also real, and all the other diagonal elements will be imaginary, ZQ. Okay, this can be used for calculation of S matrix of two hole directional coupler. Usually an short note or detailed note is asked in the exam. Write a short note or detailed note on working of two hole directional coupler with the use of S matrix. In that we have to mention all these things. Okay, so this is about two hole directional coupler. That's all for today. Thank you.